right. I guess we need to go ahead and get started. Ah, crap. I just I just closed my book by accident. My electronic book. Anybody have any questions before we get started? I know it's only two of you. Uh, but if you have any questions, by all means, go ahead and blurt them out now and type me your first and last name. I see both of y'all done that, so I didn't need to remind you. Alex, do you have any questions, bud? All right. So last time we worked
I'm all good. Oh,
on
sorry.
uh, go ahead, Alex. Sorry.
I, I was trying to say I'm all good. I just couldn't press the mute button.
Okay, no problem. Well, last time we worked with that version of Coulomb's law for electric fields. I want to recap that in a second, and I want to do one more thing with it because we were able to derive some formulas. And one of the formulas, of course, was sigma over 2 epsilon naught, which we did for a circular disk of charge. And then we imagined the scenario in which the radius was way, way larger than the distance z from it. That's more or less the scenario in which you're dealing with an infinitely charged plane. And in that limit, basically, the electric field strength resulted in or became sigma over 2 epsilon naught, where sigma is the charge per unit area. Epsilon naught is, of course, the epsilon naught from Coulomb's law. And now I want to show you what happens if you take two infinite plates like that and charge one positively, charge the other one negatively by the exact same amount, and then put them next to each other. Uh, that is a typical electronics device. Anybody know? Do either of y'all Are either of y'all familiar with what kind of device that is when you take one plate and you charge it up with a positive charge, and then you take another plate and you charge it up with a negative charge, exactly the same size, and then put them close together like that? Y'all know what that's called?
Would that be a conductor?
Close. And I'm thinking
Capacitor?
you're
Sorry.
thinking, there you go. That's the word. Yeah, capacitor. So yeah, that's a capacitor, and I just wanted to touch off on that just to get started. So let me get started with that, and then we'll jump into Gauss's law, which is the new chapter we're starting today, chapter 22. I have made chapter 22 homeworks available, and I've set the due date to for your class. It's going to be due Wednesday night of next week. That's what I currently have it set to. So hopefully that's sufficient because it's really a chapter that we're only supposed to spend a single day on. Then that's mainly because after that we do voltage, and then after voltage we do capacitance. And when I do voltage and capacitance, both of those chapters require us to use Gauss's law some more. So we end up getting plenty of experience from it that way. All right, so to rehash exactly what we have regarding the electric field, I want to rewrite those equations in vector form, so that's what I'm going to do now. So first off, the electric field came from Coulomb's law, and Coulomb's law was originally of this form: F is equal to either K Q1 Q2 over R squared, where Q1 and Q2 are point charges, and R is the distance between Q1 and Q2, and K is a constant, which is 8.988 times 10 to the ninth Newton meter squared per Coulomb squared. And the force acts parallel to the line connecting Q1 to Q2. So remember, Q1 and Q2 are supposed to be point charges. So if you draw a line connecting point one, Q1's point charge to Q2's point charge, that creates a line that has a definitive direction and all that sort of stuff. And depending on whether the force is attractive or repulsive, it will be parallel to that line pointing one way or the other, one way for repulsive and the other way for attractive. Of course, like charges repel and unlike charges attract. This can also be written with the more traditional constant, in which case you get Q1, Q2 over 4 pi epsilon naught r squared. And now I'll go ahead and write that K is 8.988 times 10 to the ninth Newton meters squared per Coulomb squared. And then alternatively, if you want to use the other version, which is what I use, then it's 8.854 times 10 to the negative 12th coulombs squared per Newton meters squared. So that's those two constants. What we were able to find is that we can define the electric field to be the limit as Q approaches zero of, and I'll just write it with the K because that makes it easier, K, Q, Q over R squared divided by Q. So that's really what it's supposed to be. And from that, we were able to get that the electric field for the Coulomb's law version of the electric field was either K Q over R squared RQ over 4 pi epsilon naught R squared. And that, of course, left us with the idea of what exactly is the direction of this electric field. And remember, we had 2 points that could define a line when we did Coulomb's law for the force. Now we have electric field, and that seems to only have one charge, so it seems to only have 1 point, but it actually has 2 points. And that's the key to understanding the direction. When you calculate this electric field, you have to calculate the R value, and the R value is the distance between the point charge, is what we're imagining capital Q to be. The distance between the point charge capital Q to the point P in space where you wish to know the electric field, that is the R. And not only that, that defines 2 points. So that line connecting the point charge Q and the point P in space that you wish to know the electric field at, that creates a line that we can say the electric field will be parallel to. And if you need to see which way it goes, it could be parallel this way or it could be parallel that way. When you go to do that, what you have to do is decide, well, if I put a positive test charge, a positive point charge in that point P where we're calculating the electric field, which direction would that positive point charge be compelled to move? And when you figure that out, that's the exact direction of the electric field. That's defined as the direction of the electric field. So that's how all that works. Now, I was able to make this into a vector equation by doing the following. E turned out to be equal to, and I'm going to stop using the K at this point. I just want to go ahead and use what is the more normal thing that we would use. So, oops, I'm getting ready to lose. Yep, there it goes. That would be the normal thing to use. So what I'm going to do is I'm going to say that there's a charge Q, and then there's a 4 pi epsilon naught, but now I need a vector that actually points in the direction of the electric field, and that vector is RP minus RQ. So remember, I told you guys that we had to imagine a vector that points from the origin to the point P at which we wish to know the electric field. That's the RP vector. And there has to be another vector that points from the origin of our coordinate system to the charge Q that's creating the electric field, and that's what our RQ is. And then, of course, the natural thing is that the distance between them, between those 2 points, is in fact the magnitude of that vector. But because we have the magnitude of that vector in the numerator, we can't just write it 1 over r squared because now we've got an extra magnitude of r on the top, so we have to write it as 1 over r cubed. So that is it. And then if we were wanting to just use a continuous charge distribution, then we'd say the differential electric field is equal to dq times rp minus r dq. Notice how I just changed from rq to r sub dq. And then all that will be divided by 4 pi epsilon naught rp minus r dq cubed. And that is the formula that I used last time and where it was able to derive various results from that. However, we had to make use of the fact that dq is either going to equal lambda dl or it's going to equal sigma dA, or it's going to equal rho dV. And just to let you know, the lambda is a charge per unit length, so that should have units of coulombs per meter. And if it's uniformly distributed over a one-dimensional object, then that lambda is supposed to be a constant. Similarly, the sigma is a charge per unit area, so that should have units of like coulombs per square meter. And if it's uniformly distributed over a two-dimensional surface, then that sigma should also be a constant. And then finally, if the charge is distributed through a volume, then rho is the charge per unit volume measured in coulombs per cubic meter, and dV would be the differential volume element, just like dA was a differential area element and dL was a differential length element. And rho, of course, if it was uniformly distributed, would be a constant. Now, what we were able to find last time is for a plate, so the electric field due to a or an whoa Nelly due to an infinitely large plate with a surface charge density sigma is E equals sigma over 2 epsilon naught. And to make it a vector, I'll just say it's in the n hat direction, and n hat means a vector perpendicular to the plate. So I did derive this last time. It became quite a bit more complicated formula. It was sigma over 2 epsilon naught k hat times, I want to say it was 1 over the square root of r squared plus z squared minus 1 or something like that in parentheses. So those last two terms were in parentheses, but when you take the limit as the radius is much, much larger than z, the distance away, you got this little result. So now I want to imagine a scenario in which we have one plate that is, say, like this, and then we have another plate right next to it. So this is two plates. This one would have, let's say, a charge of negative sigma, and this one would have a charge of positive sigma, and they're a distance d apart. And they have an area, let's say A, that'll come in handy later. But the main thing right now is they have equal but opposite charges. Now, if we look at this straight on from the side, then what I'm going to do is I'm going to mark the positive charge plate as being red. So I'm going to say this is plus, 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 plus. And then there's going to be the negative plate, and I'm drawing it much farther apart so I can fit the stuff between it that I need to fit. This one's going to be a negatively charged plate. Okay. Now, what we need to do to calculate the electric field around these two plates, remember this drawing to the right is just us looking straight onto the edge, whereas the one to the left was when I was looking at some angle so I could see more than just the edge of the plates. Uh, just thinking about the red plate, so completely forget about the purple plate. If I were to tell you to tell me what the magnitude of the electric field is due to that red plate right there, or actually, ask you the direction. What direction would the electric field due to that red plate point at that red dot that I just drew? Anybody? By the way, those of you who came in late, you might want to go ahead and chat me your first and last name if you haven't done so already. Anybody have a idea? Again, just thinking about the red plate, what direction would the electric field caused by the red plate point? Would it point to the right, to the left, to the up, to the down, into the page, out of the page, up and to the right, up and to the left, down and to the left, down and to the right? What? Anybody? So it's a big positive plate, and that means, remember, I just finished telling you the definition of the direction of an electric field is the direction that a positive test charge would be compelled to move if you located it at that particular spot. If I put a positive test charge at that red dot, it would be compelled to move to the right as a result of that red plate. So that electric field is in fact sigma over 2 epsilon naught and points to the right. If I happen to have put a dot right here, can anybody tell me which direction the electric field again would point as a result of the red plate? Forget about the purple plate. The purple plate doesn't matter. We just want to know what direction the electric field would point at that other red dot and then also at this red dot. So this one on the far right here, anybody know what direction the electric field would point over here due to just the red plate? Yes, that's right, Alex. Because again, the plate is positively charged. So a positive charge that we put over here on the right hand side of that plate is going to be compelled to move away towards the right. Now, if I put a positive charge right here at this dot on the left hand side, we would see that that one would point to the left and its magnitude would be sigma over 2 epsilon naught. Again, we're going on the assumption that these dots are closer to the plate than they are to the edge of the plate. And that's the key thing here. That's what makes it approximately infinitely large. Now I want to do the exact same thing for the purple plate. So the purple plate is going to create a electric field as well, and I want to know what direction the electric field will point uh, between the two plates, to the left of the two plates, and to the right of the two plates. Anybody want to tell me between the plates which direction the electric field due to the purple plate would point? Purple plate would point is not easy to say. Okay, so the purple plate is negative. Again, we're ignoring the fact that the red plate's there. We're just trying to do one at a time. So the purple plate is negative. That means if I put a positive point charge between the two plates, it would be compelled to move towards the negative plate, and that means it would point to the right, and the quantity or the strength of that would be sigma over 2 epsilon naught. Similarly, if I were to put a positive test charge over here to the right of the two plates, then that positive test charge would be attracted to the plate and therefore it would run off to the left. So that one would be sigma over 2 epsilon naught as well. And then similarly, if I put a positive test charge over here on the left hand side of the two plates, that positive charge would be compelled to move towards the negative plate, and therefore it would be sigma over 2 epsilon naught here. So now we can see how these electric fields act in these three regions. In the region on the left, we get E equals 0 because sigma over 2 epsilon naught to the right plus sigma over 2 epsilon naught to the left add to give you 0. Similarly, on the right hand side of the two plates, that would also give me E equals 0 because sigma over 2 epsilon naught to the right plus sigma over 2 epsilon naught to the left gives you 0. Now, in between, it's quite a bit different, and we end up getting between is sigma over 2 epsilon naught plus sigma over 2 epsilon naught would just become sigma over epsilon naught. And that is, in fact, the definition or the actual result of the strength of the electric field between a positive and negative plate of equal charge per unit area sigma. Equal but opposite, of course. Any questions on that? That was sort of the last thing to finish up chapter 21. Of course, I already showed you the result that we got for the electric dipole, so I'll recap that real quick and then move on. So we define the electric dipole as a positive charge Q and a negative charge negative Q, a distance d apart, and we imagine a vector that points the opposite way of the resulting electric field, and that vector would be long enough to point from the center of the from the center of the negative charge to the center of the positive charge. That vector we're calling d, and then there is a electric dipole moment p equals electric dipole moment, and P is defined to be Q, the positive magnitude of those two charges, times the vector D. Notice the vector D points in the opposite direction that the actual electric field points, because the electric field caused by these charges would compel positive charges to run away from the positive charge toward the negative charge, and therefore would point in the opposite direction of the D vector I just showed you. But we've defined it this way for a good reason. When we do define it that way, then we can imagine this electric dipole in an electric field, and when we do that, we discover that the electric dipole experiences a torque in that electric field, and that torque is given by P cross E, which is the typical cross product that we learned about in 241. And we also learned that the electric dipole would have a potential energy given by negative P dot E. So those things are important. Those are actually how we work. For instance, when we try to treat something like a polar molecule, like water, for instance, in a human body, when you're using an MRI device. So if someone actually gets inside of an MRI, the water molecules are going to act like they have a specific charge. One side positive, one side negative. It acts like an electric dipole, and there's a magnetic field obviously created at the MRI. That's magnetic resonance imaging. It's technically nuclear magnetic resonance imaging, but you can imagine that that would also cause an electric field. And in some sense, if you submerge these electric dipoles in electric field, they'll align to it because of this torque and potential energy. And then if you flip the direction of it, then that dipole will flip as well, and that gives off some energy signal and all sorts of good stuff. But not only that, there's ultimately going to be another result where we get mu, the magnetic dipole, is equal to basically an area times a current. So it's going to be an area A times a current I, and that current is going to have a specific vector associated with it, which I'll just call n hat or something like that. When we do that, what we discover is that, in fact, the torque on the magnetic dipole is mu cross B, where B is the magnetic field, and the potential energy of that magnetic dipole in a magnetic field is negative mu dot B. So notice the exact similarities between the electric dipole and the magnetic dipole. That's a key thing to understand. But that's all we did last time for chapter 22, and we'll say, or chapter 21, excuse me. We'll say this ends chapter 21. Okay, so that brings us to chapter 22, which is Gauss's law. So there's chapter 22 is Gauss's law. And Gauss's law is actually kind of a neat thing that was discovered basically while they were working on electricity, magnetism, and they didn't necessarily know that there was a link between electricity and magnetism. They knew there might be, so they of course investigated it, and they kept finding similarities. So they thought more and more that it was going to have a lot more interlinkings, and it ultimately did. What we ultimately reached the conclusion was that the electric field and the magnetic field are just two opposite sides of the same coin. Meaning, in one reference frame, you might say, hey, this particle is doing A, B, and C because it's a charge in an electric field. But then you jump to another reference frame in which that charge is actually, say, moving, and the only way you can explain the same motion that you saw in the other reference frame is that now that particle in this new frame is experiencing a magnetic field that causes the exact same result that the electric field caused. So that's what I mean when I say that the electric and magnetic fields are just two sides of the same coin. And that's ultimately what we were able to discover. And I say we, I mean people more brilliant than me. I'm just able to follow what they did and to some extent and can work out the math a little bit. Uh, but in doing that, what they discovered was a concept of flux. So Michael Faraday was one of the first people to actually imagine that charges in space would cause an alteration to the space around it, and that's what we now know of as our electric fields. Now he couldn't do too much with it because Michael Faraday had almost no mathematical background whatsoever, but he was a brilliant scientist and could think very analytically and geometrically and stuff like that. So he still pondered the idea of these electric fields, and he actually saw them as if they were little tentacles reaching out all over space. So when you see a point particle that's positive and you got these little arrows leaving from it, those are the electric field lines. He actually imagined those actual field lines existed. And when you start thinking about it that way, sometimes you can get some nice mechanical analogies that work out really well. And what Maxwell tried to do when he did finally publish his equations that later became known as Maxwell's equations. He tried to make mechanical analogies because that was sort of the trend of the time. Some people actually took that as bad, and that they literally just chose not to study it because they thought that was an old timey way of looking at things, and it was a branch of mathematics they didn't know about. So they were looking for all sorts of excuses not to study it. But Maxwell pressed on, and luckily, Maxwell died at a really young age, so he didn't get as much publicity and fame as he should have. But luckily, he had some acolytes in what they call the Maxwellians, and those people went on to show the value of Maxwell's equations, and all they had to do was put them in this vector calculus form. So that's where we're going. But one of the weird things is we came up with Gauss's law, and to come up with Gauss's law, basically what they were taking is they were imagining these little field lines that would leave electric charges, and they took them very seriously, and they imagined there was some scenario where you could sort of take a field line and just find the component of it that's perpendicular to like a window, say, and that became what we call electric flux, and that's what I got to talk about first. So before I do that, I want to give you a picture of field lines around a charge. So for instance, if we imagine that we had a charge right here, and this charge was, well, let's say lowercase q, okay, and it is positively charged, so I'll put a positive there. Well, that means something. That means that the electric field lines, if I imagine putting them a fixed distance away, that fixed distance is going to be two squares. Then if I did that, then I would find a field line at two units away, always has the same magnitude, and that magnitude I've drawn here as two squares. Okay. I didn't take the time to calculate whether two squares would be reasonable or not. I'm just going with it, and then we'll compare it to another charge in a second. Now, that would be the charge Q, and I really shouldn't have put the lowercase q here because obviously that made it problematic to see. So I'm going to sort of pretend like it's not there and erase it. Okay, so now I have that, but again, this is just a charge q. So that charge is q. Now, if I drew another charge that has a charge of, say, 2q, then that's going to be a little different. I'm going to show you that now. So if this one was a charge 2q, which again is still a positive charge, and let's see if I can move this over to a little bit. Oop, I did not mean to do that. Okay, so this charge is going to be a charge 2q. Okay, that's a 2, not a z. The same thing happens, except now this charge is twice as big. So, in some sense, we have to recognize that the electric field should be twice as large. So, to do that, what I'm going to do is say, okay, here's the electric field line at 2 squares away, just like we did before, and it still has a length of 2. Don't worry, I'll show you how it makes up for that in a second. So this is the electric field, but I'm going a little further in that because it's twice as big of a charge, I am going to say that it's going to have twice as many electric field lines as the single charge. And that looks roughly like this. Now, all those arrows are supposed to be exactly the same length. I eyed it and tried to do it, and they're all supposed to be anchored at the exact same distance away so that the tails of each of those vectors are on a circle whose center is the center of that charge 2q. Okay. So that's a key thing to understand when you're actually looking at point charges. If one charge is q and the other one's 2q, you need to express that by the charge 2q having twice as many field lines. Not only that, if the charge was negative, it would be quite a bit different as well. So, for instance, let me show you what a negative charge would look like. If I had a negative charge like this, and that charge is in fact negative q, then what I can imagine is that the electric field line at a distance of 2 squares away would now be not only the exact same length as the last one when I did positive Q, and not only the exact same number of actual field lines, the only difference would be is that now it's pointing towards the charge. Okay, so that's a key aspect. You look at positive charges as sources of field lines, and you look at negative charges as what we call sinks or drains of field lines. So you would imagine, for instance, a bathtub or a sink. You would have a source of water, which is the faucet, and then you'd have a sink for the water, which is the drain. And from that, the equations that we use for fluid mechanics turn out to be a lot like the equations we use for electricity and magnetism, and they have sources and sinks, and certain very specific things come from them. So that brings us to the next idea of now that we have field lines and we understand numerically how they're related to the individual charges, we can now introduce the concept of flux. So electric flux is given the symbol capital phi. It's electric flux. And it's in some sense a count of the number of field lines that are perpendicular to a hole or a surface or something like that. So, for instance, when I want to talk about a electric flux, then we might imagine something along the lines of this. Let's say we have a window in space, if you will, And perpendicular to that window, we can imagine there's a vector. And that vector A has the magnitude of the area of that window. So, for instance, if this window were 2 meters wide and 3 meters tall, the area vector A would have 6 square meters as the magnitude. The main thing is this vector is definitely going to be perpendicular to the surface of the window, like that. Then, if we have an electric field line, let's say that comes along at this direction. Oh, I should probably draw it in a different color. Okay. If it came along, say, in this direction, then there would be a small angle theta. It doesn't have to be small, but in this particular drawing, it's obviously small. There's a small angle theta that the electric field line E makes with the area vector A. The area vector has to be perpendicular to the, if you imagine this blue frame as like the frame of your screened in windows, then the screen or the glass window, if you had a storm window, the glass of that would be the actual surface, and then the area vector would be perpendicular to it like that. Okay, that's by default. Now, there's no good reason for A to point this way as opposed to this way. Notice perpendicular from the back side would be like this, or perpendicular from the other side would be like that. Both of those are acceptable, and we make no claims as to which one's the appropriate one. So it doesn't matter at all right now when we're dealing with windows to calculate the flux as to whether the A points, from the front side towards us or from the back side away from us. That just doesn't matter. Later, we're only going to apply this flux formula to closed surfaces, surfaces that have a clear inside and outside, and then we can arbitrarily choose the area vector to point as if it points from the middle out. Okay, that's what the definition is going to be when we have a closed surface. So we'll have a definitive answer when we use the closed surface, but when we're using a plain window like this, we don't have such an answer. So we have to just sort of use whichever one we wish. Now, what is that flux? Well, in order for us to choose the component of the electric field that is actually perpendicular to the surface, in other words, perpendicular to that window surface, we have to basically take the component of the electric field that's parallel to A. And if you look at it this way, I'm going to draw a little bit more and complete a right triangle here so that you could then see that this is a right triangle, and we could imagine the electric field as having one component parallel to A and the other component perpendicular to A. The component parallel to A would be given by E times cosine theta. So we're going to say E, well, let me go back to my color I was doing. We're going to say the flux is the area A times E times cosine theta. That is the actual formula for the flux. So notice how by just doing this operation, we get the idea that we're going to take an A vector and we're going to take an E vector. We're going to take the magnitude of the A vector, the magnitude of the E vector, and then multiply them by the cosine of the angle between them. And that's going to give us A, the area of the window, times E perp, which is the component of the electric field that's perpendicular to the window. So with that in mind, I'm going to say this part right here is uh, this part right here is E perpendicular to window, or it's E parallel to A. Okay, so it's the electric field component that's parallel to a vector, or you can think of it as the electric field component that's perpendicular to the window. They both mean the same thing. And if you remember from last semester, there was a operation that we did with two vectors that gave us the magnitude of one vector times the magnitude of the other vector times the cosine of the angle between them, and that was in fact the dot product. So we can see that the flux is actually A dot E. So that's another way of writing the flux. Now, ultimately, what we'll do is we'll want to not consider just a simple flat electric or window like this one. We'll actually want to consider a whole surface that could be, the surface of a baked potato if you wanted, or the surface of a volleyball with all the grooves and all that stuff. And at every point, you'd have to imagine cutting the surface up into smaller and smaller rectangles until they are actually flat. In other words, you've cut it up so small that that particular part that might have had a lot of curvature, you're now zoomed in so much that it's completely flat in that one little area, and then you have exactly one little area vector that represents that because it's now flat. Now, if you've gotten it small enough, there's a good chance that the electric field at every point in that window will have exactly the same magnitude and direction. If it's not, then you have to maybe divide the window up even smaller parts so that you can get a single electric field vector that is close enough to exactly the electric field vector at everywhere in that itty bitty window. And then you calculate E dot A for that little window. Then you go over to the next adjacent little itty bitty rectangle, do it again, next again, next again. That's basically an integration that you're calculating. So that ultimately the flux becomes the integral of E dot dA, where we're going to imagine instead of having just one big window, we might have, for instance, a surface that looks like this. And notice this is a curved surface, and we're trying to make it get small so that it looks completely flat, not unlike the earth, how it feels flat even though you know it's a sphere. The same thing's going on here. So we can imagine cutting this uh, chunk of curved space up into maybe this itty bitty rectangle right here, in which case there's my little differential area element, and it's now called dA just because it's infinitesimally small. In other words, it represents an infinitesimally small area A that we're now calling dA. So the area inside of this little rectangle is dA, and then the vector is dA with a vector. It has to be perpendicular to that surface, and its magnitude has to be equal to the area of that surface. Then you could compare that, let's say, with the electric field going through this way, and it would have an angle theta. And because of that, you could basically, if you've gotten it small enough, the electric field would be the exact same vector all places in that itty bitty rectangle, and therefore you could just calculate it for that whole rectangle. E times A times cosine theta. And then you go to the next little rectangle and add that one. And then you go to the next little rectangle and add that one. And what you're doing is an infinite sum, which is exactly what an integral is. So that's the big picture. Notice that shape that I showed you was a curved surface, but it wasn't a closed surface. You still have the same arbitrariness where the DA could have pointed it out like I have it drawn, or it could point the opposite direction, and that would be perfectly acceptable. But once we get to closed surfaces, that ambiguity will be gone, and we'll just be able to choose whatever direction we want. So, for instance, when we go to a sphere, I'll draw that real quick just to give you an idea what we're thinking of here. So, for instance, if I had a spherical surface, okay, there's an attempt at a sphere, and of course, I'll let the program try to make it a little neater. So this is an actual spherical surface. Notice that has a clear inside and outside. Now, when you break up this into an infinitesimal little rectangle, let's say this one right here, there's no longer any ambiguity about which direction the A vector should point. Because this is a closed surface, we're automatically going to draw the A vector, which of course is going to be a dA. We're going to draw that pointing as if it comes from the center and points out. So that's the key. Once you have a closed surface, then there's no ambiguity. You can only point the vector outward from the surface, not towards the inner part. So there's your little dA. And in fact, you might even recognize that if you guys have ever seen spherical coordinates, you'd probably recognize exactly what the area of that little rectangle is. If you don't, that's okay. You'll get to it in Calc 3. And I've actually got in my helpful documents and links module, and actually also in week 0 module, there's video links to show you the Cartesian coordinate system, the cylindrical coordinate system, and the spherical coordinate system. It's highly useful for you to recognize the symbols that we use for those, because I can teach Gauss's law a lot easier if I can use some of those tools, like the individual unit vectors. In Cartesian coordinates, it's just I hat, j hat, and k hat, or x hat, y hat, and z hat. Those are the unit vectors in Cartesian coordinates. In spherical coordinates, you have an r hat vector that points radially outward. You have a theta hat vector that points uh, basically azimuthally, and then you have a phi hat vector that points polar wise downward, and those are all unit vectors as well. And these differential area elements and these dA vectors, they are very useful to indicate the directions of those. So that's why I would like you to look over cylindrical coordinates and spherical coordinates. All right, now let me show you an example of how to calculate flux, at least in the simple case. I'm going to go to example 22.1, and it says, calculate the electric flux through the rectangle shown in figure 22-1A. The rectangle is 10 centimeters by 20 centimeters. The electric field is uniform at 200 newtons per coulomb, and the angle is 30 degrees. So they had a drawing more or less like the drawing that I had just now. I'm going to draw it like this. That one went down 3 and over 1. I'm going to go down 3 and over 1 like that. So this is the little window we're talking about, and we're going to assume that maybe this side is 20 centimeters and this side is 10 centimeters. And then we're going to imagine that there's a vector that's perpendicular to this and represents this surface. Oh, I don't know what happened there. Ooh. Okay. And it represents this surface as follows. That vector, again, because it's not a closed surface, we could pretty much arbitrarily point it one direction or the other. In this case, I'm trying to show you that it's perpendicular to the surface. That's our area vector A. And obviously, the magnitude of A is equal to 10 centimeters times 20 centimeters, which equals 200 square centimeters. Now, I actually dropped my pen and must have wrote on here by accident, so let me get rid of that. All right, so there's our area vector. And then what they have is an electric field vector, E, and the magnitude of the electric field vector is 200 newtons per coulomb. Okay. And this angle between them is theta. And according to the problem, theta is 30 degrees. And what they want to know is what is the electric flux. Later, we'll subscript this with an E and the another one with a B because there's going to be a magnetic flux as well. But right now, we're just doing the electric flux. And that's going to be E times A times cosine theta. So our flux is in fact 200 newtons per coulomb times 200, whoa, Nelly, times 200 cubic, or excuse me, square centimeters times cosine of 30 degrees. Now, you could go ahead and make this instead of 200 cubic centimeters. We could put it in the SI system of units, which is really what we want. So instead of using 200 cubic centimeters, I'm going to do zero point 0.2 times zero point 0.1, which gives me 0.02 zero, and that is square meters. So I'm going to use the actual square meters figure instead. So when I take 200 and I multiply it by zero point 0.1 times zero point 0.2, which obviously is the 0.02, and then I multiply that by the cosine of 30 degrees, I get 3.46. Oops, I should stick to the color I was using. That gives me 3.464, and the units are Newton meter squared per coulomb. And of course, we only had at best two sig figs, so I should probably underline the 6 and the 4 and realize that this is the electric flux that we're trying to calculate. Anybody have any questions on that part? So there's some weirdness in electricity and magnetism that makes this quantity to flux really important. And in fact, it turns out that it's really important to vector calculus anyways, because there's something called the generalized Green's theorem and stuff like that, which basically is a fancy vector calculus equation that says that if the amount of stuff in a closed volume is increasing or decreasing, that amount of stuff has to be represented by a flux through the surface of that closed container, right? So it basically says, hey, if if your bag of potato chips is losing weight, then it's clear that you can find the exact weight of the potato chips that's being lost by discovering exactly how much potato chip mass is flowing through the front side of the bag, the back side of the bag, the side of the bag, the other side of the bag, the top of the bag, and the bottom of the bag. That's ultimately where all this Gauss's law start stuff comes from. So, anybody have any questions on that one? Now that we have this idea of what flux is, and I've even generalized it to show you when it's, over a curved surface or even a closed curved surface and stuff like that, there's some other things that we might want to take into account. So, for instance, if you consider a single point charge like this, and then you imagine it inside of some volume, maybe a kidney bean shaped three-dimensional object, something like this, okay, then there's a way we could actually determine the flux from that surface. Okay. In other words, the amount of electric field lines leaving that surface. Well, all you have to do is remember, hey, this is just like a charge Q. So I know that field line's going out that way, that field line's going out that way, that field line's going out that way. And it turns out that the number of field lines, which represents the magnitude of the charge, remember when I did 2Q, I got 8 field lines, whereas when I did a single Q, I got 4 field lines. Well, that stands to reason that if you actually submerge the single plus Q charge inside of a kidney bean shaped area like that, then you expect the number of field lines to pierce the surface of the kidney bean to be directly proportional to the charge. And that would be exactly right. It turns out that the electric flux through a closed surface is equal to the charge enclosed divided by epsilon naught. In other words, the constant of proportionality between the number of the charge and the number of field lines that permeate or penetrate the surface is 1 over epsilon naught. Okay, that's a key aspect. Now, if you look at this and then say, well, wait a second, what if I were to have a positive charge right here and then a kidney bean shaped three-dimensional surface here? Okay. Well, you can see what would happen. Specifically, there would be a field line stabbing that way, a field line stabbing this way. And what you'd see is this field line actually entered there, but then it seemed to exit there. And that's the norm. It turns out if you don't have an actual charge inside of the kidney bean shape, then the total number of field lines that enter it is equal to the total number of field lines that exit it. So therefore you get the net flux is zero, which is also consistent with the equation that I wrote up here that said the electric flux over a closed surface is Q enclosed over epsilon naught. In this case, I had zero charge enclosed, so I get zero lines penetrating the surface. Additionally, if you had something a little bit more exotic, like a plus charge and a minus charge, then you know what the field lines would do. The field lines would point this way, this way, this way, this way, this way, and this way. Now, if we put a kidney bean shape around it, and again, it doesn't have to be a kidney bean, it could be any arbitrary closed shape, but I'm just trying to show that it's a three-dimensional shape, not a two-dimensional shape. And maybe this is the shape that we're going for. Like that. Now you sort of see, oh, it looks like every charge or every electric field line that is emanating from the positive charge is going to disappear on the negative charge so that we might get a zero number of lines that penetrate the surface of the kidney bean. And that's exactly what happens again. The flux is equal to the total charge enclosed. In this case, I had a charge of plus Q plus a charge of negative Q. If you add those two together, you get zero. So this would have zero flux. And this one was the same thing. This one, on the other hand, would equal Q over epsilon naught is equal to the flux. Okay? Because the charge inside of there was Q. And of course, these charges are plus Q and minus Q. So that's why we got zero there. Any questions on that? All right. Now that we have that and we've done a couple examples, I'm going to state what Gauss's law is, but I'm going to start off by calculating it. So the flux, as we said, was electric flux is equal to the integral of E dot dA. Now that's the definition of the electric flux. But if we want to calculate the electric flux over a closed surface, then we do something special. We say electric flux through a closed surface. Again, closed surface just means that there's a definite inside and outside. Unlike a toilet paper roll, if you actually pull the cardboard out of a toilet paper roll, you could argue that outside is outside and inside is inside. But then you'd realize you could take your finger touching the outside of the toilet paper roll and poke it in the hole in the side. Then your finger's on the inside. So that is not a closed surface. However, if you put a piece of cardboard on each end, then it would make a closed cylindrical surface, and you'd have to actually cross cardboard to get from the inside to the outside. So in this case, it's if we wanted it for a closed surface, darn it, then the electric flux becomes phi closed surface is equal to the integral E dot dA, but this time I put a circle over it because it means that I'm only supposed to evaluate this integral over a closed surface. So that's what the little circle on the integral means. It doesn't make you do anything different from the vector, I mean, from the integral that you're used to doing. It's just a matter of knowing that it's applied to a closed surface. So what I'd like to do right now is think about a point charge at the origin. So let's imagine right here I have a point charge at the origin. So this will be my x axis. This will be my y axis. This will be my z axis. Notice that is a right hand coordinate system. Remember your right hand coordinate system. If you hold your right hand up, this is the x direction, this is the y direction, and this is the resulting z direction. If it matches that, you're good. If it doesn't, then you're wrong. Okay. So now what I'm going to do is I'm going to take a point charge and stick it inside, or a spherical charge, because that's also equally valid. I'm going to put it at the origin of this coordinate system. So here is my point charge at the origin, like that, and it's a charge of Q. Darn it. So this charge is Q. I don't want to put it down there because I need it to, I need to actually use the space around that to draw something. So what I'm going to do is I'm going to try to think about this charge, positive Q, and I know that if I go exactly 2 squares away, then I'll have an electric field that'll be the same strength everywhere at that distance away. So 2 squares away from the center, 2 squares away from the center, and 2 squares away from the center would be right here. Those are my electric field lines. I'm going to go ahead and draw all 8, though, just because I can. So this would look also like that. This would look also like that. And this would look also like that. Now, what I would like to do is I would like to create a closed surface around this charge Q such that the electric field is always exactly perpendicular to the little A vector that represents the little segment of the whole surface. So I'm trying to imagine a closed surface where the individual electric field lines will all be perpendicular to the individual area vector lines for each little part of that surface. From this, we can see that the spherical symmetry of the charge would suggest that a closed spherical surface would be a really good choice. So that's what I'm going to do. I'm going to surround it by a Gaussian surface. That Gaussian surface is going to be a sphere, if I can ever draw a sphere properly. It's going to be a sphere centered on the origin. There it goes again. Still didn't draw it. It's supposed to make a circle for me, but it's not doing it. Darn it. Stop it. Draw it again. What? It's making me mad. It keeps messing up. Okay, so there's a spherical surface, and you can see at least along those lines, every little area vector or every little electric field vector is exactly perpendicular to the surface. That's what I'm trying to show you with all this. Obviously, I didn't draw my diagonal electric field lines that great, and I even screwed up a little bit on some of the ones that weren't diagonal. But the main thing is you see that the electric field is not only perpendicular to the surface for each of those cases, but it's also all of them have the exact same magnitude, so that the E is in fact a constant on the surface of this sphere. Now, the sphere, we might say, has a radius, let's say R. So this distance from here to here is R. And what we've discovered is that with this sphere, we're going to have, like, for instance, if you looked up at one particular chunk of area from that sphere, you would see the actual area vector would point this way, and then you'd see the electric field vector would point that way. Because of this, we see that the cosine becomes the cosine of zero, and the cosine of zero is one. So we end up just getting E times A. But in this case, since we had divided the A up into such a small area, it's technically a differential A. So that's what it looks like everywhere. So when I go to calculate the electric flux here, what I know is the magnitude of the electric field. So at R equals R, the E field strength is E equals Q over 4 pi epsilon naught R squared. And that's just from our formula for the magnitude of electric field due to a point charge Q. So that's what the electric field is going to be. And we can now calculate the flux. So the flux through the surface is equal to the closed integral of E dot dA. Now, the E is going to be, as I said, Q over 4 pi epsilon naught, and it's going to be evaluated. This integral that we're doing is technically what we call a surface integral. And to be honest with you, I've never known anyone that took Calc 3 and got far enough. But in principle, it's in your third semester of calculus where they do surface integrals and line integrals and stuff like that. But I've just never known of a class to reach that far. Because I didn't get to go to Ivy League schools, maybe, but I don't know. But the main thing is, this is a calculation you should do. And the way you do a surface integral or a line integral, in this case, it's a surface integral. So you got to evaluate the integrand on the surface. So I have to put R squared down there because at the surface of the sphere, the R distance, which is the distance from the Q, is R, the radius of the sphere. And I know that the direction of the electric field is that it points radially outward, and that R hat vector is the vector that represents radially outward. Okay, it comes straight from spherical coordinates. Similarly, the differential area element, I could actually tell you what that is in terms of spherical coordinates, but you don't really need to know. The important thing is you know that its magnitude is dA, and that since it's parallel to E, it too must point in the R hat direction. So that is what the calculation of the flux is supposed to be. So, with this in mind, what we can do is we see we're going to integrate some dA, the Q, the 4, the pi, the epsilon naught, the R, the big R squared. All of those are constants, so I can pull them right out in front of the integral. So I'm going to get Q over 4 pi epsilon naught R squared. All that comes out in front. And not only that, The dot product is what we call a linear operator. So that little dot is a dot product. And a linear operator means that you can take all the scalar parts of those two vectors and put them way out in front and then just let the dot product act on the actual vectors. So that's what I basically did. I took all the q, the 4 pi epsilon naught, the r squared, and the dA, and I pulled that out to the left of the dot product. And then I was just left with r hat dot r hat. Now remember, a dot product A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. Now remember, dot are vectors with a little hat on them represent unit vectors. So could anybody tell me what r hat dot r hat is? What's the magnitude of r hat? Anyone? Remember, I hat was a vector that we used, and that was called a unit vector. And j hat was another one that we used that had a hat on it. That was called the j hat unit vector. And k hat is a unit vector pointing in the k direction. X hat is a unit vector pointing in the x direction. Y hat is a unit vector pointing in the y direction, and z hat is a unit vector pointing in the positive z direction. So whenever you have a hat on a vector, that means its magnitude is anyone?
One.
Exactly. Thank you. I knew somebody would get it. So the magnitude of r times the magnitude of r is 1 times 1, but the two vectors are identical, so the angle between them is 0. So I get 1 times the cosine of 0 degrees, which is just 1. So lo and behold, r hat dot r hat is just 1. And all we have left is q over 4 pi epsilon naught r squared times the integral of the differential area element on the surface of a sphere, and we're integrating over the whole sphere. So the area of the actual integral should work out to be the surface area of a sphere. And of course, the surface area of a sphere is 4 pi r squared. So now you can see that the 4 pi cancels out with the 4 pi, and the r squared cancels out with the r squared. And lo and behold, just like I told you, we got the electric flux is equal to Q over epsilon naught. And lo and behold, Q is exactly the charge we had inside of it. So there's a pseudo derivation, if you will, of Gauss's law. So Gauss's law is this. It says the closed integral of E dot dA is equal to Q enclosed over epsilon naught, and the Q enclosed means the all of the charge inside of the Gaussian closed surface that we chose. When we go to use this Gauss's law, we're going to use it in a very odd way in this course. We're using the integral form of Gauss's law, which is what I have written there in blue. And the trick for this is Gauss's law is always, always, always true. It's not called Gauss's helpful hint that sometimes is true or sometimes works. It's called Gauss's law, so it clearly works all the time. But this weird way we're doing it only works with certain symmetries. What we're going to do is we're going to make hypotheses based on our knowledge of Coulomb's law of the form of the electric field, and due to any kind of charge distribution, then we're going to hypothesize a Gaussian surface such that the electric field on that Gaussian surface is one perpendicular to to the Gaussian surface and therefore parallel to the dA vectors, and 2 is a constant on that Gaussian surface. It turns out those two are the same thing. There's no way you can be one without the other. But then, in addition to that, any other parts will actually have the dot product equaling 0. So we're going to never, ever, ever have to do an integral on the left-hand side. We're, in some sense, doing one, but we're doing one that we know exactly what it's going to come to be because it's just electric field magnitude times an area magnitude. The right-hand side is where we're going to have difficulties doing integrations because sometimes the Q will be the integral of lambda dl, or the integral of sigma dA, or the integral of rho dV. So that's how we're going to work it. Let me go ahead and show you an example. So first off, we're going to consider the electric field. I'm doing example 22.3. It says a charged conducting spherical shell. A thin spherical shell of radius r0 possesses a total charge, capital Q, that is uniformly distributed on the surface on figure 2211. Determine the electric field at points outside the shell, B inside the shell, and C if the conductor were a solid sphere. Okay, so I don't have much time. We're only like 5 minutes from class, but being over. But I'm going to do it rather quickly, hopefully. So what I have here is a spherical shell. I'm going to try to use my program to draw this as appropriately as we can. So I need to go from there to there to there to there. There you go. So there's my spherical shell, and it has on top of it a total charge Q, and its radius, of course, is R0. So Gauss's law says this: the closed integral of E dot dA is equal to Q enclosed over epsilon naught. Now, this is a weird way we're working with an equation. I'm solving for the integrand, and I can't solve for the integrand until I have the left-hand side done and the right-hand side done. So the first thing I do is I write LHS for left-hand side, and that's the closed integral of E dot dA is equal to, but I'm going to make a hypothesis first. So I'm hypothesizing an actual Gaussian surface and an electric field. First, I got to guess or hypothesize what the electric field is going to be like. Well, it appears that this spherical surface of charge has all the charge uniformly distributed on the outside edge of that surface. So I suspect the electric field has spherical symmetry. So I'm going to say E is equal to some electric field that only depends on the distance r, which is the radial coordinate, from the origin, and that it points radially outward. So there's my hypothesis. I said it's a function that should only depend on r, which is the distance away from the center of the sphere and therefore the origin, and that it should point radially outward. And then I'm going to draw a Gaussian surface, and that Gaussian surface I want to be defined such that it can have an electric field that's going to be a constant on it, and therefore it will be perpendicular to the surface. So I'm going to now draw my Gaussian surface, which is another sphere, because that's the only shape that I could imagine that fits the bill. So this green shape is my Gaussian surface. And it is technically a sphere just like the blue one is. Now, because of that, I can calculate the left-hand side is equal to the integral of E of r hat. Now I've got a dot product that with the dA. Well, the dA, actually I should probably draw that in green. The dA is just going to be dA in the r hat direction. So I'm going to write this as dA r hat. So left hand side again. I should have wrote that down there, but I'm just redoing it now. So the left-hand side, E dot dA, is equal to the integral of E of r hat dot dA r hat. Now, because we're on the surface of the sphere and the sphere has a radius r, that's the Gaussian surface has a radius r. Let me draw that in green just to make sure everybody understands it. So the Gaussian surface is a sphere of radius r, and because we're doing a surface integral, the E has to be evaluated on the surface of that sphere, and that surface has a radius of r. So this is going to become E of r, and it's a constant, so it can come out in front. And then I've got the integral dA, and then I have r hat dot r hat, which we already know is 1. And we know, therefore, that the left-hand side is E of r times 4 pi r squared, because that's the area, the surface area of a sphere. Now we do the right-hand side, and the right-hand side is just Q enclosed over epsilon naught. Well, the total charge enclosed is Q, so I'm just going to write Q over epsilon naught. Now I set left-hand side equal to right-hand side. That gives me E of R times 4 pi r squared is equal to Q over epsilon naught. And this, of course, is just for the area for r greater than r0. I still have to do two more parts for the other one, but I just want to get this one part done. So now I can see that the electric field we hypothesized, E of r, is in fact Q over 4 pi epsilon naught r squared. And by hypothesis, that means our electric field, E, is equal to Q over 4 pi epsilon naught r squared r hat. And this is technically for r greater than r0. So all I have to do now to do for r less than r0 is I draw another spherical surface inside, but you're going to see that the electric field inside would be 0 because the Q enclosed in that case would be 0. But that's enough for right now. When we see each other again on Thursday, I'll finish up the rest of these examples for this chapter, and then we'll move on. And that should give you plenty of time. Thank you for coming, everybody. Make sure you chat me your first and last name if you haven't done so already. You're free to go, and I'd like you all to go ahead and contact me if you need anything. Hopefully, y'all saw my emails about the face-to-face tests and the various times I can proctor those for you. So let me know if you need any help with that. And if you have any other questions, just stick around and ask them. I'm going to wait for the last person to leave before I split. But thank you for coming, everybody.
Test is still in person, not
Yes.
not online respondus.
No, no, but there is a
Okay.
way. I did send out a announcement where there's some times I have where I can proctor it for you via Zoom. So that's a possibility. So check your email and your announcements that I sent out.
Okay. I was gonna show up early because obviously I have to do it in the lab because I don't have a laptop, but I need to show up early to do it because I can't stay late because I have chemistry right after.
Okay. What time did you send? I did see an email that someone had sent me that they were planning on coming tomorrow. Was that you that sent that?
I sent it via text, not email.
Oh, okay, gotcha. This is you're Shannon Graben. Gotcha.
Yes. I
Okay,
wanted to
yeah.
make sure that I'm good and I don't have to take it online using the video camera tonight.
No, no, and you can if you
Okay.
wanted to. I'm actually available this morning as early as 8 in the morning. Tomorrow morning as early as 8 or 8:30 if you'd like to take it before lab. I know it's not your lab day, but that's an option as well. You can come at
It
either
is
do
my
that.
lab
Yeah.
day tomorrow.
Oh yeah. Is it tomorrow?
Yes, it is.
I thought you were
242.
in. Oh, that's right. You are in PHY 241, aren't you?
No,
No,
I'm
you're
in
in 242.
242.
That's what
I
it was. Okay.
survived.
Yeah, gotcha. No problem, Jamie. Well, yeah, you can show up early if you'd like, because I'm going to be there by 8, and
Okay.
some people might even take a paper test instead of a computer test.
Okay. So, okay, so there's options.
Yeah.
Okay. I just wanted to make sure that I don't need to do it tonight because there is no way for me to stay late tomorrow because I have chem lab after that.
Gotcha. Yeah, no problem. Your class starts at 12:20 right after lab, or your class starts at 2 o'clock right after, after a gap after lab. But you could do it during the lab. You could do it before the lab. You could
As
do
soon
it
as we're done with the lab.
as soon as you're done with the lab. Any of those times will be fine.
Okay. I just wanted to make sure because yeah, I don't want to have an issue with chem.
Hmm.
I have 3 exams this week and it's like you're
Yeah.
you're kind of the middle one, so I'm like, okay, what am I doing? The other thing is I'm having a small problem doing the propagation of error lab.
Okay.
Namely that Microsoft Word keeps freezing.
Uh, there's, I don't know any reason you need what Microsoft Word to be able to do anything if you just want to print it out at school and work on it by hand and then, scan it later. That'd probably be better. There's really no need to have to use Word,
Okay.
but basically Word needs the equation editor package to be
Yeah,
used as
I'm
well.
using the equation editor and it's just every single equation I add makes it hang more.
Hmm. Yeah,
It
that's
is
very,
hating it because there's too many of them.
yeah, that's an ongoing problem with Microsoft.
This is why I do my chemistry lab reports in Google Docs and
Yeah.
then download them.
Well, just print it at school if you want, and then do it by hand, and then just take photographs, make them PDFs, and turn them in that way. That'd probably be
Okay.
easier for you. Okay.
Okay. Thank you.
All right. Thanks for coming, Shannon.
I
All right. Hey, Colton, I did get your message. I responded to one of them, and the other one I didn't respond to yet because I was waiting. I'm trying to hear back from students. I might be able to change the time to meet your schedule on Saturday or Sunday. Are you sure you can't even make it on any of the scheduled times that the testing center has on Monday or Friday or anything like that?
Can you hear me? Are you able to hear me?
Yes, I can hear you.
Yeah, so it's kind of difficult with my ODU schedule because this past week I'm kind of like screwed over because I'm in the program at ODU and we have program like certain like research projects we have to go. We're going out on a boat tomorrow, so I have no time at tomorrow at all
Hmm.
because he has us on a boat researching and analyzing sediment all day. So,
Gotcha.
but Thursdays I go there for about like maybe 3 or 4 hours. I don't know if you're able to like, I don't know. Thursday's kind of tight though.
Oh, I'll look back at your schedule. I might even be able to do something on Thursday that matches your schedule. I'll just let me think about what's going on tomorrow, look at your schedule some more, and see if I can get back with you. But
Okay.
keep looking for times that they might have at the testing center because the testing center do have some night times. They do have Saturday
Hmm.
times, but it's for different campuses or whatever. So
Yeah,
keep
because
looking for something that fits in your schedule. If it doesn't, I'll figure out some way to proctor for you.
yeah, because of course I already have my work schedule. So I normally work on Fridays 12 to 8:30. And then Saturday I'm a 7:30 a.m. to 4. It
Right.
would be nice if I had like a, I don't know if there's an opportunity to take it at night on Saturday, or in the morning on Sunday because I work 12 to 8:30 on Sundays.
Right.
Um, but of course, then I go back to my normal ODU schedule, which is Monday through Thursday.
Yeah, on your next face-to-face test, I put all these, in the syllabus on a certain date, and you have that whole date. So you need to make sure you make your work aware that they have to give you, some time off during
Hmm.
that week for the next test where you can actually do it. Because I can't,
Yeah,
I'm
yeah,
already did it
yeah.
in like 6 different hours, so I don't want
When
to.
when is that second test? Just so I
It
know.
says it on the syllabus. Let me see if I can pull the syllabus up real quick. Uh,
'Cause I think it
so
was March or something.
face-to-face test two is due by 3/23, so it'll be that week beforehand. And I think 3/23 might be a Sunday. If that's the case, then it's probably going to be the 24th as well. So any week prior to 3/23, you just need one of those days off that the testing center could accommodate you, and therefore you could not be at work.
Okay.
So,
Yeah, more than likely, like Tuesdays and Thursdays, I tend to have a whole lot more time coming back from ODU.
right.
That's normally the days I take time to study for certain things, but of course, I have it perfectly lined up to where I have your class at 5:30 on Tuesdays and Thursdays, so I
Mhm.
can get to that. Um, so I have like maybe like a 2 or 3 hour gap, but it
Yeah, just
also
try to find
depends
one
on,
that fits. You have to find out whatever testing center is closest to you, find out what their hours are, and then make sure you take some time off, or the work gives you some time off during those hours so that you can
yeah,
actually
of
make it to
course.
one of those, or come to my class, which normally I'll have on a Wednesday. So
Okay.
if you did Wednesday, you could come at any of those times, like I sent you on the last one, which is like
Is it
8,
at
eight
five?
thirty, 9.
Okay.
There's also
So
a
it's in the
12,
morning.
12:20 to 1:50, all those different times.
You don't do you do a 5:30 class on Wednesdays by
I
chance?
do a class, but I'm literally doing a class, so I can't proctor a test at that
Mm-hmm.
time. So that's the only problem.
Yeah,
And I thought it was a
yeah.
little late because my class normally I'm supposed to be over by 7, but a lot of times I stay as late as 8 getting everything done.
Mm-hmm.
So that might be the problem here.
Yeah,
But yeah,
Mondays
just
and
let me know.
Wednesdays, I normally have like a 2 to 5 p.m. class, and I get home normally reasonable time, like around like 5:30.
Yeah.
But
Don't
of
worry. I'll figure out some
course,
way to get you this week, but just try a little better next week. I mean, next time when we do the 3/23 phase two, face-to-face test two, just try to see if you can let work know, a week ahead of time that, hey, I need,
yeah, of course,
X day off, Wednesday or Thursday or Friday or something.
yeah. Could literally just Mondays and through Thursdays is all my college time, and then work is always Friday, Saturday, through Sunday. Those are the only days I can really work, depending on the type of I work at a car wash, so
Gotcha.
it's not like crazy stuff. Sometimes I'm studying at work
Yeah, but
at
you
the
need your money,
car.
right?
Yeah, yeah, and I drive a crazy car, so
No problem.
my gas goes away pretty quick, 9 miles per gallon.
Yeah. Yeah, I used to have a truck with a well, actually, I got another truck now with a really big engine. It's the same thing. I get about 9 miles to the gallon. So
God, what truck are you running?
I've got a 350 with a 7.4 liter.
Oh boy, oh my goodness,
So,
Jesus! I have a 2007 Coyote Swap Mustang,
oh, there you go.
and it burns fuel like crazy.
Yeah, I get you. Well, like I said, I'll work with you. We'll figure out something for this
Okay.
time. I'll send you an email and let you know like one of those times that fits into your schedule, and we'll work it from there. And hopefully, we'll have better success next time.
Yeah, of course. I can make it work the next time. Just I know where and when it's gonna be, so I'll definitely work my schedule around it. I
Okay.
could this face-to-face test kind of like crept up on me because I just had a bunch of exams the past week. So
Yeah. Yeah,
I
that
wasn't paying
tends to
too much
happen.
attention.
I get you. It's not a big deal, but don't worry about it.
Yeah. Well, thank you.
No problem. You have a good one, Colton. I appreciate you letting me know. And like I said, I'll work with you. We'll figure out something.
Okay, thank you.
All right. Have a good one, buddy.
You have a good day
You too.
or good night.
That
All
too.
right.
All right.
Bye-bye.
Later, bud. Bye bye.
Later.
All right. That should be it. Bye, everybody.